Hello and welcome to the final part of Lesson 8. The aim of this video is to give you some examples of how some fluids form filaments and how some fluids don't form filaments, and to show you how those fluid filaments subsequently thin. We're going to examine the behaviour of water first of all, which is a low viscosity Newtonian fluid with a very high surface tension. Afterwards, we'll look at the behaviour of three different polymer solutions, two of which are dilute and one of which is entangled. We'll see that there's a variety of different behaviour that can occur, some of which can invalidate filament thinning data. All the experiments you're about to see were carried out on a custom-made high-speed filament thinning rheometer, the TreeMaster HB4. So, let's start with water. So the video you're watching is the filament thinning of water, and as you can see, there is no filament to thin. There's immediate breakup. So this video is taken at 18,000 frames a second. The entire breakup process is pretty much over in 250 microseconds. So water, remember, has a viscosity of 1 millipascal second, a surface tension of about 72 millinewtons per meter. So I'd like to highlight some of the particular behaviours that we see in that video in these freeze frames. So this first freeze frame is when the pistons are still moving away from each other. We can see that there's a liquid bridge between the upper and the lower piston, but this isn't a fluid filament that's about to thin. This is a fluid filament that's about to detach, because if we look at the next frame, we can see that the pistons are still moving, and we'll see that the piston position here, which are those vertical cylindrical shanks in the top and bottom of the image, will be different in the next image. But before the pistons have stopped moving, we can see that surface tension is pinching off that fluid filament at the top and at the bottom. So if we look at the next key image, we can see that that fluid pinching has indeed resulted in a detached set of droplets. And note here the beautiful symmetry around the central axis, just showing how precise this instrument is. If we look at the next image, we can again see a beautifully symmetric image of two droplets which have now broken up under the action of surface tension, and now the pistons have finally stopped moving. The next image is where those two droplets combine and create an oscillating droplet that is beautifully placed in the centre of the image. That oscillating droplet is determined, or its mechanics are determined by a combination of surface tension and viscosity. So here is the first example of how a fluid doesn't form a filament and how we can't use capillary thinning rheometry to determine anything about its nature. So let's look next at a fluid that does form a filament and where this capillary thinning rheometry can give us very useful data. So this is a solution of guar gum. It's a dilute solution of guar gum at 2 grams per litre. The frame rate of the video is the same, 18,000 frames a second, and the entire filament thinning process is finished in about half a millisecond or thereabouts. But we can see a beautiful cylindrical fluid filament is formed. Okay, it waves about a bit, but that fluid filament thins over time and then breaks up. So this is a very good filament to analyse. The only challenge is a bit wavy, and so that comes down to an image processing problem. So let me take you through some of the highlight frames here. Firstly, the fluid filament forms. The pistons are fully retracted top and bottom, and we have a beautifully cylindrical filament of fluid, which then narrows over time. So the filament diameter becomes less and less and less again until it almost subsequently breaks. Now, the highlight that I've put on this final image is to show you a phenomenon called beads on a string. Here you can see that there's a tiny little blob of fluid suspended in the middle of this filament. This is very, very mild beading. Beading is a behaviour that we see very often with viscoelastic liquids, and one that usually disrupts the ability to take useful filament thinning data, because the dynamics of what's happening in the filament above and below the bead actually have changed from the dynamics that you'd see in just a purely cylindrical filament. But up until the onset of beading, this is a very nice experiment. We could get some good data from this. So let's have a look at another dilute polymer solution. This is a polymer called RTM24. Again, the video is taken at 18,000 frames a second, and this takes a long time to thin. So the entire process of thinning in this case takes about 2.5 milliseconds or thereabouts. The pistons have stopped moving and the filament is very, very slowly thinning, as you can see. The filament form in this case isn't as nicely cylindrical as with the guar gum. However, the central portion is pretty decent, and this would give us good filament thinning data. So we can see finally the filament is getting close to the point of breaking, and there we have filament breakage and detachment of that fluid filament to form two discrete lumps of fluid on the top and the bottom piston. So again, let me take you through the key frames of this. The fluid filament forms, and it thins, and it thins, and it thins some more, and it thins a bit more and then breaks. So this, in many ways, is an ideal fluid to be able to get good data through capillary thinning and breakup rheometry. So this is great. So let's look at one final polymer solution. This is now an entangled solution of guar gum, more about polymer solutions in later lessons. And we can see that really the appearance of this fluid filament is not very good. It's disjointed, it's lumpy, it forms beads on a string. It's not going to give very good data because where is the narrowest point on this fluid filament? It's entirely variable because there's so much lumpiness within the fluid filament as it forms, as you can see here again. So let's take some key frames from this. To start with, we get a fairly uneven fluid filament forming. Now, whether this is just bad dispersion or as a result of the entanglement is up for further investigation. These experiments were done quite a long time ago. However, what this does show you is an example of when you shouldn't really be taking filament thinning data for a particular polymer solution. This would give you very bad quality data. So as a fluid filament thins a little more, again you can see this inhomogeneity within that fluid filament. Again, if you look at the symmetry of the fluid pools on the pistons top to bottom, they're not particularly symmetric. So all in all, this is going to give you pretty bad data, and you wouldn't really use any filament thinning data from an experiment like this. You just couldn't trust it. And again, there you go, the final image is another bead on a string. So the object of this short video was to give you some examples of what you see when you do capillary thinning rheometry. And we've seen 4 different examples, and one of those examples didn't form a filament. Water, the first video, is very low viscosity, it's very high surface tension, and we had end pinching occur at either end of the fluid filament as it was forming, but it never became fully formed because whilst the pistons were still moving, the fluid filament detached and became a series of droplets that then merged. The other highlight I hope that you take away from this video is how adding very small amounts of polymer, 2 grams per litre is 0.2%, to water gives you an entirely different rheology. We saw this in the way the fluid filaments form and subsequently thin, both with guar gum and with RTM24. With more polymer added, we could see the onset of instabilities, such as beads on a string, and also that very great homogeneity of the fluid filament in the first place. So I hope that's an insight into some of the data that you can take with capillary thinning rheometry.